Welcome to the lecture on third lecture on nodal analysis. In this class, I am going to explain how to apply nodal analysis to those circuits that contain voltage sources that are connected between non-reference nodes. Before going into the lecture, please I request all the viewers to go through the description section. In the description section, I provided a link through which you can download the PowerPoint presentation of the lecture which I am going to explain in this video. Myself, Satyanarayana Vanapalli, working as Associate Professor in the Department of Electrical and Electronics Engineering, Guntur Engineering College, Yanamadala, Guntur. Now, coming to the lecture, in the previous class, based upon the type of nodes or the potential voltage assumptions, I told that these nodes can be classified into two categories: a reference node and non-reference nodes. So if you look at the circuit, a voltage source is connected between a node, two nodes. So we see whether the 5 volts voltage source is connected between a node and a reference node or between two non-reference nodes. So as a fundamental rule or thumb rule, in most of the general cases, we consider the bottom node as the reference node, or if you observe the bottom node, 4 elements are connected. That means to the bottom node 4 branches are connected, and for the top nodes only 3 elements are connected on the left hand side, 3 elements are connected on the right hand side. So bottom node is to be treated as the reference node, so that this 5 volt source is connected between two non-reference nodes. So now coming to the concept of supernode. So what is the difficulty in analyzing this kind of circuits that we need to look at first? If you observe the circuit diagram, the 5 volt source is connected between two nodes. It is not possible for us to determine the current delivered or absorbed by this voltage source, so that it would be difficult for us to apply or write Kirchhoff's current law equation either at node 1 or at node 2. So this difficulty can be overcome in two ways. The first way, by assigning some unknown current to the flowing current voltage source and write the Kirchhoff's current law equation at node 1 and node 2 and solve the equations, find out the current that was delivered by or absorbed by this voltage source. This would be a tedious process. So the second one is remove the branch and write Kirchhoff's current law equations at node 1 and at node 2 by excluding the branch in which independent voltage source is present. This is the second method. So second method is a little bit easier compared to the first method. So now we come to the definition of supernode. A supernode is formed by combining two non-reference nodes between which voltage source is connected. so that sum of currents leaving both the nodes is 0. So keep this point in view. Now we try to see how the concept of supernode is applied to finding out the unknown voltages of different nodes of a circuit. Before going into the application part, let me review the nodal analysis or the supernode analysis once again. The first step in application of this nodal analysis is we need to count the number of nodes, and then we need to designate a reference node. After that, we need to label the node voltages. Next, the second step, if the circuit contains a voltage source, form a supernode about each one. Next, write Kirchhoff's current law equation for each non-reference node and for each supernode that does not contain the reference node. The fourth step is relate the voltages across each voltage source to the node voltages. Then express any unknowns, that is currents or voltages other than the nodal voltages are present. Then you need to express them in terms of appropriate nodal voltages. After that, organize the equations and solve the system of equations for obtaining the unknown node voltages. Now, this is the circuit which we have taken for our analysis. If you look at the circuit, you are asked to determine the node voltages and branch currents for the circuit shown in figure. Here I am going to explain you how to determine the node voltages. Once we determine the node voltages, it would be very easier for you to determine the branch currents. So I am not considering that part of calculating the branch currents because it is a simple substitution in the formula. Okay, so the first step of our problem is to identify the nodes. So bottom node is treated as the reference node, and the left hand side I am considering it as node 1, and the right hand side I am considering it as node 2. Let V1 is the voltage of node 1 and V2 is the voltage of node 2. If you look at this diagram, this will give a clear understanding for you. The node 1 is designated with a rectangular box, red color, a dotted rectangular box, and its voltage is designated as V1, and node 2 is encircled by a rectangular box in green color, and its voltage is V2. And in between node 1 and node 2, an independent voltage source is connected, so that it is not possible to, it would be difficult for us to write Kirchhoff's current law equation at node 1 or at node 2. That's why I am formulating a supernode by combining node 1 and node 2. So the supernode is identified by a blue colored rectangle box. Second one, formulate the supernode. So supernode is formulated by combining node 1 and node 2 with the removal of branch in which that voltage source is presented. Now if you look at this diagram, the voltage source is removed. Here you assume that the currents are leaving at the nodes. So that I1 is the current that was flowing through 1 by 2 ohm resistance. I2 is the current that was flowing through 1 by 6 ohm resistance, and I3 is the current that leaves from node 1, and the same I3 is leaving from node 2 that flows through 1 by 3 ohm resistance. Here we try to write Kirchhoff's current law equation for node 1 and node 2. That means write the KCL equations separately for the both the nodes. So 4 amperes is entering the node, I1 and I3 is leaving node 1. So that I1 is equal to V1 by 1 by root 2, I3 is equal to V1 minus V2 by 1 by root 3. So V1 minus V2 by 1 by 3 plus V1 by 1 by 2 is equal to 4. So after simplification, this value is equal to 5V1 minus 3V2 is equal to 4. Similarly, Kirchhoff's current law equation for node 2. I2 and I3 are leaving and 9 amperes is entering. So I2 plus I3 is equal to 9 amperes. Now the value of I2 is equal to V2 by 1 by 6, and I3 is equal to V2 minus V1 by 1 by 3. So V2 minus V1 by 1 by 3 plus V2 by 1 by 6 is equal to 9. After simplification, this value is equal to 9V2 minus 3V1 is equal to 9. Next, combine the KCL equations at node 1 and node 2, because we need to write the Kirchhoff's current law equation for the supernode. That's why I am combining both the equations. Thereby, I am going to get it as 5V1 minus 3V2 plus 9V2 minus 3V1 is equal to 4 plus 9, 2V1 plus 6V2 is equal to 13. After that, you write the voltage equation for the removed branch. The removed branch is 5 volts independent, contains a 5 volts independent source in it, and it was connected between node 1 and node 2, whereas node 1 voltage is V1, node 2 voltage is V2, and the positive terminal of the source is connected to node 1, so that V1 minus V2 is equal to 5. So now we got two equations. The first equation is 2V1 plus 6V2 is equal to 13. The second equation is V1 minus V2 is equal to 5. You organize the equations and arrange them in matrix form. Use Cramer's rule to find out the values of V1 and V2. So that V1 is equal to delta 1 by delta, V2 is equal to delta 2 by delta. After calculation and substitution of the values of delta 1 and delta 2, we got V1 is equal to 5.375 volts and V2 is equal to 0.375 volts. So as we determined the values of V1 and V2, you can find out the values of branch currents that are flowing through the branches. 1 by 2 ohm I1 is equal to V1 by 1 by 2, that is equal to 2 V1, and I2 is equal to 6 V2, and I3 is equal to 3 into V1 minus V2. So with the knowledge what you have gained, I hope you would be comfortable in solving some of the examples by your own. Here I am giving the practice example 1, and you need to find out the voltage V4 across 25 ohm resistance. You take the center node as the reference node. With respect to this reference node, you try to find out V4 value. Here, as you consider this node as the reference node, 100 volts is connected between two non-reference nodes. In the practice example 2, I have included a voltage dependent voltage source connected between two nodes. In this example also, you take the bottom node as the reference node and try to find out the voltage value VA and power dissipated in 2.5 ohm resistance. That means you need to find out the voltage across 5 ohm resistance, that is the node voltage of this node and current flowing through 2 ohm resistance. Once you find out the current flowing through the 2 ohm resistance, then you can make use of the expression power dissipated in the resistance is equal to I square into R. With the help of that equation, you can find out the power dissipated by 2 ohm resistance. So, with this, I would like to conclude my lecture. Before concluding the lecture, I request you to subscribe my channel so that whenever I upload any new videos on these concepts which I have explained earlier, or any other new concepts, you will get notifications so that it would be helpful for you. Thank you very much.